Welcome to EDU World Space.
So problem 8.23, we've got a couple of masses here on the frictionless table, and there's a spring between them that's compressed, and as you might imagine, these masses will be released and the spring will expand and cause them to be shot off in opposite directions. So far so good. And we have the various information we need here, the masses of the springs, or of the masses, I'm sorry. The masses of, we can pretend they're boxes. The masses of the boxes, are they equal? The spring constant of the spring, and it's important to note, this is given in newtons per centimeter. And so we're going to need to take care of that. When we put our numbers in so that we don't get wacky results, because the equations only work if everything is in the SI, non-fractional and multiple SI units. And then the spring is compressed from its resting length L that we don't care about by 20 centimeters. This again we have to be careful with. And so now we want to find what the speed of these boxes are. Now, the momentum is conserved. So here we have zero momentum. And here we have momentum of these two things going off in opposite directions. But they have equal masses. And so that means that their speeds have to be the same. So we only need to worry about the speed of one mass. And for example, all of the potential energy stored in this spring is going to be converted into a total kinetic energy shared by these two. And again, because of the speeds have to be the same, because the masses are the same, each one is going to get half of the potential energy from the spring to go into its kinetic energy. So if we start writing things down, we know that the potential energy in a spring is 1/2 times its spring constant times the square of the amount it's been compressed or stretched by. And since we know all these things, let's just work that out. Now this works out to be 175 newtons per meter. And now you could either just actually go through with, sort of a complete sort of unit conversion here, or you can just intuitively think if it's going to be 1.75 newtons in a centimeter, then if you stretch it a meter, it's going to have to be 100 times that. And it can save yourself a little bit of bother writing things down if you recognize the sort of what the actual meaning of this whole thing is. And then similarly, we have 0.2 meters is 20 centimeters. This one is a little bit easier to think about because there's nothing in the denominator here where it makes it a little bit harder to think about what's going on. And so the energy that's initially stored in the spring is 3.5 joules. So since we said already, we argued that each of the boxes is going to have an equal speed, and therefore its kinetic energy will be equal, because the masses are equal, which is why their speeds are equal to begin with. So then the kinetic energy one box gets is just going to be half of that, which is 1.75 joules. Now we know the K, and we know that that's equal to 1/2 mv squared, and right here's the thing we're looking for. So the mystery is nearing a solution. And so doing the algebra, we get 2 times the the kinetic energy. Important to make sure this is a capital so you don't confuse it with the spring constant, divided by the mass. So 2 times 1.75 joules, and these each have a mass of 900 grams. And then running that through however you like to crunch the numbers, we find that each box is moving with a speed of 1.97 meters per second. And so the velocity of this one will be negative if we call this the positive x direction, and the velocity of this one will be positive.